Okay, so now we move on. We talked about three-dimensional space from section 9.1, three-dimensional coordinate system. And now we're going to talk about vectors. So vectors are important because they, applications in engineering and physics often involve vectors. A vector can represent a push, for instance, or a pull. In how many have seen vectors maybe in a physics class? How many have seen a vectors used for like a force? Forces. Okay, Jimmy has. For tensions and physics and statics, Yeva. All right, very good. So let's see here. Let's remind ourselves what defines a vector. So, well, first of all, let's hold on. I'm trying to highlight certain things. Here I go. That's what I want. So the term vector is used by science to indicate quantities such as displacement or velocity or force that has both magnitude and direction. A vector is represented by an arrow or directed line segment. Now, the length of the arrow represents the magnitude of the vector, and the arrow points in the direction of the vector. And this is something that is important to recognize here. Let me just highlight this. Actually, hold on, let me unhighlight it. This is what I want to highlight. Right, so we denote a vector by putting a letter in boldface or putting an arrow above the letter. So like in your work, when you write a vector, use the arrow notation. Hold on here. Like this notation here. That's how you'll write a vector on your paper. But in the book, the way a vector is denoted is, hold on here. Let me just, one moment. In the book, the way a vector is denoted is in boldface letter. Okay, so these two vectors here, vectors v and u in figure 1, are equivalent vectors. Why is that? Because what defines a vector? Two things: the direction the vector goes in and the length or magnitude of the vector. The vectors v and u point in the same direction and they have the same length. So those are called equivalent vectors. Now what you can do with vectors is you can add them and you can subtract them. Okay, so if we go to the next page here, they show here in figure 2 three vectors, vectors AC in red, vectors AB, and vectors BC. Well, if you add the vector AB and the vector BC, you see the vector AB, the end of the vector touches the tail of the vector BC. So you add vectors tip to tail. So vectors AB and vectors BC add up to vector AC. So like for instance, if you had a, well, let's just keep it simple. That's how you add the two vectors. I mean, they go into the definition here. Okay, definition of vector addition. If there are two vectors, u and v are positions, so the initial point of v is the terminal point of u, then the sum of the u plus v is defined. And you can represent the sum of vectors very nicely with the triangle law. See, there's a vector u, there's a vector v. The vector u, the terminal point of u at the arrow there, is where the vector v begins. So u plus v then would just be like what we call the resultant vector, u plus v, in red. That's how you add vectors, and that is a geometric representation. Okay, and also there's a rule called the parallelogram law, where basically you see if you have u and v there on the bottom and v and u there on the top, the resultant vector is the same. Okay, so I mean, pretty straightforward stuff. Now, what does it mean to multiply a vector by a scalar? Well, let's look at that. Okay, in figure 7. So here you have a vector v, and then they're showing you multiples, scalar multiples of that vector v. So the vector v in blue, if you multiply that vector by 2, you get the vector 2v in red. And the vector v in blue, if you multiply that by 1/2, you get the 1/2 v on the right. But you can take a vector v and multiply it by -1, and that'll cause the vector to go the opposite direction. That's what you see on the bottom left there, that green vector. And then -1.5 v is to the right of that. So, you know, that's how scalar those are just these examples of scalar multiplication of vectors. Now, you can also take the difference of two vectors. Okay, but the nice thing about the difference of two vectors is you can treat it as the sum of the vector, like the difference between vectors u and v is the same as the vector u plus the vector -v. Okay, so this is how, like geometrically, if you want a picture to see how you subtract two vectors, u minus v, in figure 8 on the left, they draw a vector v, and they draw then the vector -v, and u plus -v, they draw u minus v. So, I mean, the geometry is kind of nice to have. Are there any questions so far? Okay, let's proceed on. Let's proceed on. So, okay. So, components of a vector. Let me just hold on here. So, sometimes you want to treat the vectors as a coordinate. And if you see there in figure 11, the vector A has components A1 and A2, and vector A reaches the coordinate A1, A2. The vector A on the right in three-dimensional space has components A1, A2, and A3. Okay, and so it reaches the coordinate A1, A2, the point with coordinates A1, A2, A3. Now, if you want to just, I mean, a lot of this is very, very intuitive here. Okay, let's keep going here. Let's keep going. So I think this is pretty intuitive. Okay, so if you want to find the length of a vector A, then the length of a vector A is just the sum of the squares of the components. Now let me just see, I'll show you that in the whiteboard. Okay, so I'm just going to draw a vector A here. Getting better at this. Okay, and vector A comes out from the origin, and it got to be careful here. what I touch. Yeah, it reaches. I don't know why it. You have to forgive me, class. I don't know why it keeps doing that. I don't know why it keeps doing that. Let me see if I can fix this problem. You see what it's doing? It's drawing like boxes, and it shouldn't be doing that. It shouldn't be doing that at all. I don't know. I really don't know what it's doing. It's like it's. All right. I'll have to learn to deal with that later. I don't want this to take up our space here. Give me one moment here. All right. Let me try this. Oh my gosh. All right, I'm not gonna. I'll have to figure this out later on how to deal with this. Blackboard, they've updated it, and there's like now I got to relearn. I got to learn new things, and this is something. I mean, they ought to be like a message or something, a thing to kind of like remove everything. But it keeps wanting to do this shading. But let's not tie up the lesson with that. Let's go back to the book. Let's go back to the book. I'll deal with that later. So what they're doing here, if you were to draw a vector A out to the coordinates A1 with coordinates A1 and A2, by the Pythagorean theorem, the length of that vector A would be the hypotenuse of a right triangle. Okay, and so the length of the vector A is just the sum of the square root of the sum of the squares of the components. That's all that is. Let me just see here. Yeah, so let me go back here to the, let me go back. You see here in figure 11, you see here in figure 11, on the left, that vector A. Well, if you were to complete a right triangle there, the vector A would be the hypotenuse of a right triangle with distance horizontal, like the bottom leg would be A1, and the leg going up and down on the right would be A2. And so the length of the vector A would be the length of the hypotenuse of that right triangle, and that would be the square root of the sum of the squares of the components. That's what they're getting at. Okay, and similarly for a three-dimensional a vector in three-dimensional space, also it's the square root of the sum of the squares of the components. So the idea of taking vectors and adding and subtracting them, well, we've seen geometrically what that looks like, but in terms of like adding two vectors, then you just add the components of the vectors to get the components of the sum of the two vectors. Okay, and that's true for three-dimensional vectors as well. Okay, I mean, is there anything here that is strange? Hopefully things are kind of intuitive. All right, so in example 4, they give you a vector A and B, and they want you to do these different operations. And they show below how to do it, how to get the length of A, how to get the vectors A plus B and A minus B, vector 3 times B, and the vector 2A plus 5B. And I hope there's nothing strange there. Okay, are there any questions? All right, let's move on. So, okay, so in how many have heard, for instance, in maybe another class, maybe a physics class, of this basis vectors I, J, and K? Okay, Yeva's seen that, and Ara's seen that, and you know these are the what we call the standard basis vectors for three-dimensional space. Christopher's seen that, Simon's seen that, and the idea is that you can take any vector in three-dimensional space and write it as a linear combination of the vectors I, J, and K. And you notice, and Ara's seen that, yep. You see I, J, and K are in bold. They're in bold, so they're vectors. And you know, here's a picture of these standard basis vectors. And so if the vector A, for instance, okay, if the vector A here, highlight all that. If the vector A had components A1, A2, and A3, okay, then the vector A would simply equal A1 times I plus A2 times J plus A3 times K. That's what it would equal. And this gives us another way to express a vector. Okay? Take a look there. Okay, that was a telemarketer. I just hung up on them. All right. Well, I didn't hang up. I said, I'm teaching, I have to go. And then I hung up. Okay, so the vector with components 1, -2, and 6, you see you can write that as I minus 2j plus 6k. And sometimes one way of writing a vector is better than, it's more convenient than the other way. It's just different ways to think about things. So what we want to do is we want to look at an application with vectors. And I have a nice application here. I mean, basically, this is the basics of vectors. And I want to look at an application here. So let me just see here. Yeah, I think I'm going to actually do this from the book, I think. Because I'd like to give you a little time to work on that next assignment as well. So in class, what I try to do, I mean, of course, I lecture and go over examples, and and help to make sure you understand things. But you know, if I can be a little more efficient, save a little time, then I can give you some time to work on things in class, like homework, and students find that helpful. So let's look at this problem here. Well, no, let's go to example 5. Yeah, let's just go through these examples here. So in example 5, they give you two vectors, and they want you to express the vector 2a plus 3b in terms of I, j, and k. Okay, so now what you would do, by the way, what you would do if you were to, well, now hold on. Yeah, if you were to write 2a plus 3b, and a and b are vectors, you're going to use vector notation above a and b. Okay, you don't write 2a plus 3b if a and b are vectors. You have to use that vector notation. Okay, because otherwise I won't know that A and B are vectors, right? And it can get very, very confusing. So in the book here, they just say, okay, well, if we want to add 2A plus 3B, they show how to do it right here. I mean, it's really it isn't a big deal. I mean, hopefully it's intuitive for you. Are there any questions on? Yeah, don't use the caret. Good question. So I know that like in some physics classes they use the caret sometimes to like. Well, let me say this the right way. Let me go back to the whiteboard. So, like, how many have seen maybe something like this for vector notation? Okay. The problem with that is, or has seen that. The problem with that is like if you take linear algebra, which is Math 284. By the way, I'm teaching that in the fall. Sometimes you have vectors that are approximations or projection vectors, or I want to say that the right way. But let's say approximations. Approximation vectors, you use the hat. So you don't really want to use this notation. I know they do it sometimes in physics, but the absolute best notation to use, tell your engineering friends, is this notation here with the vector symbols. Okay, you're welcome. You're welcome. All right, let's see here. So yeah, hopefully this is okay what you're seeing. Hopefully not a big deal here. So let's look at a few more things. Here. So sometimes we want to have. I don't necessarily need all of this here. We want to have a vector that points in the direction of a vector but has length 1. Okay, a unit vector is a vector whose length is 1. I, j, and k are all unit vectors. Well, in order to create that vector, you just take the vector A and you divide by the length of A, like they show you here. Maybe I can. That's how you create a unit vector. And the length of that vector is equal to 1. They show that below. They justify it because the multiple of the vector A is 1 over the length of A. One moment. Okay, so take a look at that. One moment. So you see, if you want the length of the vector u, that equals just the length of the vector c times the length of the vector c times a, but the scalar c can be brought then out front of the length of a, and you just get 1. So anytime you want to find the unit vector of a vector, you simply compute the length of the vector. This is example 6. Find the unit vector in the direction of 2i minus j minus 2k. Simply find the length of the vector, which is 3 in this case, and then divide the vector by 3. And that gets you the unit vector. It's really quite fascinating. Okay, are there any questions on that? Okay, one moment. Okay, let us proceed on here. Just look at something. I'm debating, there's a nice example of an application of vectors in the book, in the textbook. Okay, but I think actually I'm going to do the one in my notes with you. So let's go ahead and work through this problem here. Let me give you a moment to copy this example down. Okay, so we have here, and I'll show you a picture of this as well. But in this problem, and you'll see something like this in your homework. Example 7 is also a nice example of this kind of thing, but in this problem, you have ropes of 3 meters and 5 centimeters in length, and they're fastened to a holiday decoration that is suspended over a town square. The decoration has a mass of 5 kilograms. Okay, so the ropes fastened at different heights make angles of 52 degrees and 40 degrees with the horizontal. Find the tension in each wire and the magnitude of each tension. Okay, so the book, as I recall for this example, provides like a kind of a picture, but it might not put in the angles for it. Well, actually, it might put in the angles too. But let's go ahead and look at it. So what this picture looks like is the following. I want to make sure, does everybody have the example copied okay?
Yes.
Okay. Okay, here we go. So here's the picture of the situation where we have here. So the holiday decoration is right here, and it's being suspended. It's being suspended by these 2 ropes. Okay. The 3 meter rope is attached here, And it makes an angle of 52 degrees with the horizontal. The 5-meter rope, which is longer, is attached to a horizontal beam, say here, and it makes an angle of 40 degrees with the horizontal. Now what's happening is the weight, the holiday decoration, which has a mass of 5 kilograms, is being suspended. So it's not moving. Well, okay, so what's happening is, of course, you have the decoration, okay, wants to drop due to gravity, right? Or wants to go down, but it's being held up by the 2 wires, 2 ropes. And so you have these 2 tension forces that are T5 for the 5-meter rope and T3 for the 3-meter rope, which are acting against the weight vector. Okay, and note, we can note here that the sum, well, I want to say this the right way. The sum of these 2 vectors, okay, plus the sum of the 2 tension vectors plus the weight vector would have to equal 0. Okay, that the basically the system's in equilibrium. How many maybe have seen something like that? Maybe in a class they had this kind of all right, Yeva's seen that, Simon has. Okay, all right. Well, so in order to figure out the tensions, okay, the tension has 2 components, an X component and a Y component. So we like for the 3-meter rope, the I'm going to say this the right way. The X component of that tension vector, which is going to be negative, and the Y component of that tension vector was going to be positive. Well, if you think about like drawing a right triangle here, then the cosine of 52 degrees is equal to negative x over the length of, over the hypotenuse, which is the length of the T3 tension vector. The reason I have negative x here is because x itself, right, is negative, right? If you think of this as like the origin, x there itself, it's negative. And so negative x is going to be positive. So the cosine of 50, the cosine of an angle is adjacent over hypotenuse. So, you know, based on the right triangle here, okay, and you have this 52 degrees, right, as your reference angle, right? Let me just so I mean this is all in the recording, but let me just clear this out a little bit. Right, so here's your reference angle of 52 degrees, and the x is understood to be negative. So the cosine of 52 degrees for this right triangle is equal to the negative x, negative of that x divided by the hypotenuse. Sorry, I'm not drawing it great here, but that hypotenuse there would be the length of T3. And similarly, the sine of 52 degrees would equal y over the length of that tension vector. So if we solve for x and y, then the tension vector T3, okay, the tension vector T3 would have to equal what you see here on the right. That's what the T3 vector would have to So that's what that tension vector would have to equal. Okay. Now, similarly, you can work with the tension 5 vector. Okay. Tension 5 vector, you have a positive x here and a positive y there. Okay. And if you worked it out, the tension 5, obviously those x's and y's are different from the other x's and y's for the 3-meter rope, but the tension 5 vector would equal this. Okay, so what we have to do is we have to solve, in order to specifically figure out what the tension vectors T3 and T5 are, right? We have to figure out what the length of T3 is and what the length of T5 is. Okay, we have to figure that out. Now, we also understand that since the holiday decoration is being completely, since it's being balanced by the tension forces, then the sum of those forces is equal to the 0 vector. But that means then that T3 plus T5 equals negative W vector. And negative W vector, well, okay, what's that vector points vertically. Okay, I want to say this the right way. The vector W points in the negative direction, but negative W vector would be a vector that points in the positive J direction. So I'm taking the mass, 5 kilograms, and multiplying it by 9.8 meters per second squared. That's going to get me the component of that J vector. Where am I getting this from? Okay, what is this? This is mass times acceleration. Mass times acceleration is equal to what? By Newton's second law. What equals mass times acceleration? Force. That's right, Lexi. And the reason that the negative goes away, because the negative W vector, I mean the W vector, I'm not drawing this the best I can, but the W vector points downward, right? Based on the picture, the W vector points downward. So then the negative W vector, okay, would have to point upward in the positive J direction. Well, the component of that weight vector is equal to the whole. I mean, there's no other component than the J vector. So the entire force, the component, mass times acceleration, is the component of the J vector, and it's going to be a positive 49J because negative W here points vertically in the upward direction. So far, so good? Does that answer that question? All right. Well, so what we can do, you notice 49J can be written as 0I plus 49J. So what if we were to set, I mean, if we, we're adding T3 and T5, right? This here equals the T3 vector plus the T5 vector. I'm sorry, that's a little Maybe I can make it a little bit. Right? T3 vector plus the T5 vector. So this means the following then. I mean, look at T3, look at T5, and look at this. If this T3 vector plus this T5 vector equals this vector here, then we're going to end up with a system of equations that you see here. That's what we're going to end up with. And so now we have two equations with two unknowns, two variables, the length of T3 and the length of T5 vector. So we can solve. So what I choose to do is use a substitution. Based on the first equation, I solve for T5. I solve for T5, and then I'm going to substitute that, or I solve for the length of T5, and then I'm going to substitute that expression. See if I can make it. I'm going to take this here and substitute that in for the length of T5 in the second equation. And that's going to get me this equation. Please let me know if you have questions. Please let me know. Now I'll mention that the example in the book has, for instance, example 7 has it has a weight that's in terms of pounds. Well, pounds is already a unit of force. Okay, but in this problem, since we're dealing with metric units, in order to get the component of that weight vector, we had to use force equals mass times acceleration. Now, this is not a physics class, but there are some basic physics concepts that are going to be used from time to time. Well, what I can do in this this equation here, okay, is I can factor out the T3, the length of T3, and then I can just, solve and find out what the length of T3 is. And obviously, they're going to want it in rounded to the nearest hundredths place, for instance, 37.56 newtons. That is the magnitude of that tension vector. And now that you know what the length of T3 is, you can substitute that back in. Well, you can go back to this equation here and substitute in the length of T3 and solve for the length for T5. So it's a problem it's a beautiful problem because it draws on your knowledge of what vectors are, and it draws on your knowledge of trigonometry. Incidentally, in the ebook, in the appendix, Appendix C, there is a trigonometry section there that reviews trigonometry. How many of you have been a little while since you've used trigonometry. Hopefully it hasn't been that long, because polar coordinates has it, right? That's standardly covered in calculus too. But yeah. Okay, are there any questions before I go to the next page? Okay, so now that now we're going to take this length of T3, 37.56 newtons, and here we go substituting it. Hold on, let's blow that up a little bit. Go substituting it in that other equation, and so the length of T5 is 30.19 newtons. That is the tension in that wire. So the 5-meter wire, no, that's the magnitude of the tension in the 5-meter wire, and the magnitude of the tension in the 3-meter wire is 37.56 newtons. Okay, so now if you want to write out the tension vectors, the components of them, well, remember, this here was originally negative length of the T3 vector in front of the cosine of 52 degrees. And this here, actually, hold on. This here was, yeah, that was just the length of the T3 vector. So, you know, you get your components for that tension vector T3. And then similarly, the T5 vector, you get that. So now you know exactly what those tension vectors are. You know their components. And if you want the magnitude of the tension vectors, I'll put that in down here. Okay, the magnitude of the T3 tension vector would just be the square root of, you know, the of negative 23.12 squared plus 29.60 squared, right? And then the length of the T5 vector would be the square root. Sorry, that isn't very neat, but, well, it's neat enough, but let's make it a little better. The stylus is not always the easiest thing to write with. Okay, so now we're looking here and here. It's really a fascinating problem. Because it's an application, and you're going to see a lot of applications in this class. You're going to see a lot, which is good, right? It's always good to know where the math is used. I didn't bother to figure out, you know, what those tensions are. Let me see, maybe I can do it. One moment. Okay. Here, I'm getting 37.56. And the other one, I don't have enough room, but I mean, I think you know how to figure that out. Are there any questions at all on this? Okay, Alberto's good. And I appreciate giving me a thumbs up. I mean, basically, if you're comfortable, good. Hold on, somebody else. Yeva's comfortable. Arena's comfortable. Hold on, I'm looking at all these. Christopher, Angela, wonderful. Wonderful. Narina, Yeva, Aura, Matthew, good. Arian, Grayson, wonderful, wonderful. And Simon. Okay, well let me go ahead and stop the recording. Basically now we've covered section 9.2.